Okay, thank you, Professor Mai. And good morning, everyone. So thanks for taking your time to join my presentation. So regarding the trade-offs between electromagnetic and e-NVH performance of electric machines. So with SIMULIA Manatee. And my name is Yi, so I would like to also thank my colleague Anthony and Nicholas who helped me prepare the slides. So maybe before I jump to tech side, so I know you've heard many names here, Dassault Systems and SIMULIA and Manatee, so what are they? So maybe I give you a short introduction about us. So Dassault System is basically a software company, and so we have more than 25,000 colleagues around the world, so in 184 sites, and we support more than 330,000 customers around the world and across the 12 industries. So we have different headquarters, but the worldwide headquarters is in Paris, and we have 77 R&D labs around the world. And so we have different brands here from Dassault Systems. Maybe you heard from the modeling or the CAD side, so CATIA and SolidWorks. So we have also like Innovia for planning and Delmia for the manufacturing and also the media data for medical thing. But the most important thing is we have the SIMULIA brand. So SIMULIA means simulation. So what are we have for SIMULIA? So actually we have a bunch of products here. So like the power flow and X flow for fluid, and CST for the EM electromagnetic simulation, and EyeSight for process, for automation, and Tosca for the optimization. And also Wave6 for the acoustic simulation, SIMPAC for the multi-body or motion simulation, and the most important thing for today is we have the Manatee. So it is a specialized tool for the e-NVH simulation or e-NVH studies. And so because we cover all domains from structure, fluid to EMAG and motion, so we cross 12 industries. So for sure, the transportation mobility is also one of our focus. And also, last thing, so we cross not only the physics, but all scales, so from micro scale to the macro scale, so from element to the whole system level. So I guess that's enough from us, so maybe come to my side. So today I would like to maybe first give you some basic ideas or concepts regarding the e-NVH challenge you may face in your e-NVH design or simulation. And in the second part, I will give you a more practical example, so how to use Manatee to get rid or to solve such kind of e-NVH challenge or problems. So if we say, okay, talking to the total noise from the whole electro drivetrain or electro machine, so we can split them into different categories. So like we have 3 major sources, so like mechanical noise, so from gearbox, and also the fluid noise, so from fan, and also the magnetic noise, so from the Maxwell stress. So it is very important to assess and control all the sources at the same time due to masking effects. Because with our experience, we see some customer put really huge effort optimize the fan noise, but in the end, they find, okay, there's a problem with magnetic noise because just fan noise is too loud to cover the noise from magnetic noise. So just keep in mind, so there's masking effect is very popular in this simulation. But coming to the topic today with Manatee, so we focus only the magnetic noise. So this is the main goal or main scope for the Manatee software, and which means the device must at least have containing a rotating machine. So maybe just a little bit mathematics behind this, coming to the magnetic force. And so we just can say, if we get the magnetic force, we can do a 2D Fourier transform into 2 dimensions. So 1 dimension is space and 1 dimension is time. So if we describe space, we usually use the wave numbers. So describe the space distribution from magnetic force. What are they? So maybe I give an example. So this is the resultant force, magnetic force for a specific frequency. So we can first split them into 2 directions. So radial direction and circumferential direction. We can carry on to the further decomposition. So like now we have the different wave numbers or patterns. So that's this one, so wave number 0, we call it a pulsating or breathing shape. So which means, so all the amplitude acts at the same time, so simultaneous, so just like breathing. And we have also the wave number 8. So we have the number 8, that which means, so during time, we always say, okay, there is a 8 maximum and 8 minimum all the time. So this is also one of the shapes we will see. And if we just say, okay, we focus on the radial direction, and then now we can come to another dimension. So we are now in space, and now we can jump into the frequency or in time. So this is also one of the typical plot for such kind of analysis. So how to understand? So we have the x-axis and the y-axis. So y-axis is wave number, so it's just a spatial distribution of the magnetic force. And the mechanical order, so we also can say in frequency or in time. So we have 2 dimensions. It's because it's a 2D Fourier transform. And if we take this machine as an example, so IPMSM, 48 slots and 8 poles. So we can see that, for example, for the harmonic 8, so we have the wave number 8, so which means this, with wave number 8, its maximum, its minimum, it will dominate the harmonics on the 8. So this will be a dominant pattern or shape from wave number side, from space side. However, if we check the 48, so we have 48 slots, so we have also 48 harmonics, and this time we still have the dominant shape, but in this time we change from R equal to 8 to 0, so we are now in the position. So we can see that from different frequency time, from different shapes, we have different dominant. And if we know, okay, what is the space or wave numbers, what mechanical orders, then we can jump into the noisy part, so have better understanding on the resonance. So resonance is something we really dislike because it will amplify the noise and vibration. And when does this resonance happen? If we know, okay, if the shape, the frequency, or let's say if the space and time match the structure modes, so there will be some resonance. So how to understand? So maybe I say, okay, this is a positive force at a radial direction at 8,600 Hertz from the stator stack. So if just they unfortunately match the structure mode, so it's still positive at 8,600 Hertz, so probably we will have the resonance. So if you check this point, so it's the peak value, and we can say, okay, so Manatee will tell us the 48 will be the dominant harmonics, and we have the positive pattern or positive shape with radial direction could be a dominant one. Okay, and resonance is something also will give us really feeling because it will deliver the unpleasant noise, high-tone noise, and sometimes even just exceed the NVH requirements. So it's something we dislike, but how to get rid of that? So Manatee could be the option here. So besides the conventional method like the parameter sweep and optimization, so in Manatee we provide more than 15 techniques here to mitigate the NVH problem across different domain engineers, from control engineer, electro engineer, to the mechanical and NVH engineer. And most of these techniques do not question the initial machine design, so which means there will be a negligible torque and efficiency reduction here. And how does it look like? So if we come into the design of electric machine itself, we can like using the pole number or skewing, rotor notching to reduce the noise. And if we come into the control engineer, we can use current injection, for example, and damping for the mechanical engineer. So maybe as we also notice that for different technique here, we have different range of reduction. So Manatee is just like some platform which help different engineers from control to EMAG and to mechanical to work collaboratively in the same design, in the same GUI, in the same interface, in the same language. So they can talk with each other and they are work in the same platform. And for the presentation today, we just give you an example with the rotor notching. So here, just a short introduction. What is rotor notching? So it's just to remove some part of the rotor surface, the material from the rotor surface, and they highly used in the e-motor industry. And this will for sure influence the electromagnetic force, and thus will influence the total e-NVH performance. So for this one, this machine, no rotor notch. And this one, we have the single notch on each post. And we can imagine, so the rotor notching is somehow like the additional pattern. So we somehow modify the original pattern, so this will give us a new set of the new wave numbers and the frequency. If we put the rotor notching or new set of magnetic force in a good way, we can reduce the e-NVH. How it works, and then this coming to my second part. So we may take this machine example. So again, 48 slows and it pulls IPMSM. To simulate such kind of machine, in Manatee, we usually need the 3 basic requirements here, or 3 basic input. What are they? So the magnetic circuit geometry, so basically the CAD of the machine, and also the coil configuration, magnetic material properties, and so on. And also, we need to have the operating points. So here we have the green 30 operating points input, and with Manatee, we interpolate with 100 operating points because we want to get more points to capture every corner case of the e-NVH problem. So 30 points is for sure not enough at this stage. We also need the mechanical model. It's not only machine, it is the electrical drivetrain, so it will be some other parts. So we can provide in Manatee just like the very simplified one, 2D beam model, 2D shield model, but we can also bring the more realistic model like the FE model. So here we can include the inverter, gearbox, and so on. So once we have seen, so this is the interface from Manatee. It's pretty straightforward, user-friendly. So we have different tabs here. So like with machine tabs, we can define a machine. It's template-based. We can different design of rotor and stator, skewing, and properly something else. Once it is set, we are coming to workflow. So we set for example, the operating points. So give speed. If we use MTPA, so max torque per ampere control strategy, we need to also give the DQ currents here. And the last thing, so we need to import the model basis, so structure model. So from Manatee, we not only support the model from Abacus, but we also support the other conventional CAE tools with their structure model. This can be also imported into Manatee and orchestrate together. So once we set up simulation, finish simulation, so we can check the results. So one of the typical results is the SPL plot, so sound power level, so it's regarding the noise. So if we check first this plot, so it's not that visible, so we see the black line, so the overall line, so it's just on the top of it. And the other colored one is a different contribution from different harmonics. And from this plot, we can clearly see that, okay, so yeah, we do have the different harmonics, but each harmonics have really different contribution. So like we can see that the 48 will be the dominant one because it's almost overlapping with the black one. So this is, we know, okay, for this kind of simulation, the 48 could be really the noisy one. And what else we can see? The peak point. So like this one, so we have the peak point OP1. So from Manatee, it can give us some more information. Say, okay, for OP1, from Manatee, it will tell us the 48 is for sure the dominant harmonics, and we can see the wave number side. So it is wave number 0 positing, but in the circumferential direction. So here maybe a more detailed look, how does circumferential look like? So it's just a tangential to the tooth. And we can maybe find another noise point, so OP2. Okay, it's again from 48, we know, it's clear. But in this time, Manatee tell us, okay, it's a little bit special. We're still in the noisy positing pattern, positing shape, but we have different directions. So we are all in the radial direction. So again, even we have the same patterns here with wave number 0, but we have different direction as a dominant one. So to get rid of these 2 noisy points, and then for sure rotor notching we can use at this stage. And then once we, how does it look like for rotor notching? So we just set one single notch on the rotor surface and with specific dimensions. And then we do a parameter sweep on different notch angles, like from -15 to maximum 15. And just a side note here, so we just sweep the notch angle, not the dimension from notch, because from our experience, the notch angle have more impactful influence on the e-NVH, but not the dimension itself. So just for simplicity, we just sweep the notch angle from 15 to -15 to plus. And also we set this in Manatee, this is the interface from Manatee, and we have the 1.5 degree as increment. Okay, now what we have now, so we have the 21 candidates from -15 to 15 degree. We have also 100 operating points from interpolation. So this will describe the machine run up from 0 to maximum 14,000 RPM. And also we have the real FE model, mechanical model behind. So to run such kind of the simulation, and we can have the results in 30 minutes. So with just a laptop, we don't need the HPC at this stage. So once we finish the simulation, so we can check the results for sure. So for this one, this is for the first operating point. So x-axis is a different notch angle, and the y is sound power. So we can see, okay, this point with 7.5 has the strongest noise reduction. We like that, and we have roughly 10 dB reduction. And also, if you check the torque, so we have the 2% torque reduction. So what happens here? So you can also imagine. So rotor notching is somehow the additional gap in the rotor surface. So it will somehow increase the equivalent air gap. So air gap bigger, we have the lower torque, makes sense. But 2%, I mean, it's still negligible. And if you check the second operating point, also good. For the same point, 7.5 degree, we have a best noise reduction and slightly torque reduction. Okay, we have a good one here, so 7.5 degree. Everything good. But remember, we just checked these two operating points. So what others look like? Does this still satisfy? We can have a check on the overall operating point from 0 speed to maximum. So what we can see here, so this blue one is the one with unnotched, and the one with orange with notched one. So we can see the noise reduction almost everywhere. So that means with this rotor notching on 7.5 degree, so we have a good noise reduction. That's good. But we also know that, okay, so during notching, increase air gap, we have the torque reduction. It's very minor. But I mean, yeah, good, but not still perfect. How we can make it more perfect? Increase currents, so slightly. What we do in Manatee is we have the built-in MTP and grid smooth. So based on this notching machine, so we will give you a new set of the slightly increased currents. And then we can rerun the simulation on the notch machine. So we don't have to do the parameter sweep here. So we just, when we ended with 1.5 minutes, we get the results. So how does it look like? So we first check the torque. So now we have the actually 3 sets of the plots. It's not really visible. So we have the blue one from the one with not notching, and this one, these two with notching. The differences is the orange one with original currents and the green one with increased currents. So if we check these two, the blue and the green, so you can see that they are almost overlapping with each other. So that means with increased currents, we can achieve the similar torque or same torque as the one without notching. And in the meantime, if we check the noise, which means with increased currents, it still have the similar noise reduction. So how to understand this plot? So let's see. With increased currents, it will give us the same torque as the one without notching, but still it can give us a very good noise reduction compared with the one with torque reduction. So maybe I put some more numbers, maybe you have a better feeling. So with these tables. So we have the orange one. So this is the one with notch, and then we have the original currents. We know that, okay, with notched one, original currents, we have the noise reduction, but also we have the slightly torque reduction. So we dislike that, so we want to make it more perfect. So we have the 2% or slightly current increase. And then in this time, we don't have the torque reduction anymore. But also, yeah, the compromise would be like we have the slightly noise reduction, but I mean still very good compared with an original one. And what I didn't mention is the efficiency. So if we check the efficiency number, so the uncolored one, so in green, is the one from original machine. So this one without notching, and the colored one with notching. So you can see that, so no matter if we bring the notching here, or if we just increase the currents here, so it will have the very minor influence on the efficiency. If you still remember, so our technique for Manatee with, no matter with notching or something others, it will not question the initial design. So negligible torque reduction and also the efficiency reduction is expected. And by the way, this efficiency simulation is finished in SIMULIA CST. So let's make a short summary here. So with rotor notching, we really find a good trade-offs between the electromagnetic and the e-NVH. What does this mean? So use rotor notching, we can one side have maintain the mean torque. We don't have torque reduction, but on the other side, with e-NVH side, we have a good noise reduction. So we have a slightly silent machine. So rotor notching is a technique which usually widely used by the electrical and infantry engineer, and it will change the harmonics or magnetic force in space and time. In this case, we just studied the 48 harmonics, but if 24 is dominant, we can also for sure just optimize that. So just remember, so we have in this case had more than 8 dB reduction, but in 30 minutes with a local laptop, and without also questioning the initial electromagnetic and the mechanical design. And the last thing I was not really mentioning during the presentation is, so for this study, for this single notch, we just consider the motor in the machine in the motor mode. But what if the machine in the generator mode is will rotate in another direction? So the e-NVH performance will be totally different. So we also do a study with a dual notch. So we have 2 notches here. So with dual notch, the machine will always have a good performance, no matter it's in motor or generator. But due to the time limit, so I cannot show much details. But if you are interested in, so we can talk further on after during the break. So here to my last slide, so give some advertising. So in this afternoon with Sim Room, my colleague Anthony and Nicholas will give you a more deep dive and brainstorming on the NVH problem and share you also our experience and thoughts. And we are very welcome to you to join this session. So thanks for your listening, and please feel free to ask questions if you have.
So thank you very much, and it's a short away for me.
Jingchen from Vitesco. If you increase the current, do you increase it randomly, or you have some function to calculate how much current you should increase in D and Q direction?
Good question. So we have the function. We have built-in algorithms, a template. You don't have to worry about how to calculate. So our template will help you calculate a new set of currents directly. So you can see we have the numbers here. So we do have the not random number, but we do have the algorithm to help you exactly achieve the same torque as before.
Okay, thank you.
You're welcome.
Sorry, your microphone.
Thank you very much for the presentation. It's open.
I guess you need to turn it on.
Yeah. Okay. I want to ask a question about outside the presentation. There are temperature and direction of magnetic field effects in electrical steel or the magnetic body. What do you think about that if we consider or ignore these effects in terms of being able to matching real world results?
Okay, I can speak separately. So for the time being, we not support. I guess my temperature and the direction of magnets can be considered in Manatee. But if you want to say, okay, match the real physical world, you'll need some effort, because one side, okay, how to set up simulation is a pretty important thing. And another thing is how to set up your physical test. Because sometimes we think the simulation results are really match the one, but sometimes we have the improper setup from physical, so we need some effort. So here we have also some experienced experts from Manatee, so we can also help you to have the bench results from simulation and physical. But from our previous experience, so we have really good agreement between the simulation and the physical world.
It can be of high effects as a result. High effects on the design, or not being able to matching real world results. It can be an important effect. These effects, in your opinion, or not?
You mean the flux opening?
Direction of magnetic flux and temperature in the body, magnetic body. These are
yes.
important effects in your opinion. Yeah, okay.
Yeah, and also we can simulate such kind of thing directly in Manatee. So very different, let's say, direction from magnet, and maybe one pole is this way and one pole another way is fine also.
Thank you.
Set in Manatee.
So yeah, thank you for the presentation. I have one question. So you mentioned regarding different notches and the angles of the notches. Is it possible also using this software to determine the, let's say, precise angle which will give the highest benefit?
Yes, so this is just parameter sweep, but you can also for sure optimize. So we have the built-in sweep and optimization function, so it's not a problem.
Okay, so you don't have to provide a new geometry every time, so it can optimize it for you.
Yeah, yes, it's a built-in interface, so actually you just need to click and then you don't need to care about how the kit is modified. But actually you can also see the animation somehow in Manatee, which notch are changing. And even further, so let's say if I like this one, 7.5, I want to use for my further image study. So I don't export the card and then reuse that. I just click that and reuse, and Manatee will recognize directly, and you can use this card with notching further on. So here is always automatically programmed.
Okay, thank you.
You're welcome.
Thanks. So thank you very much. So if there are no further questions, we will go into the break. The original schedule is to restart at 10:50, so we suggest to restart at 11 sharp. So there's at least also half an hour break to refresh and also to discuss with those four interesting presentators. And then we'll see us in 30 minutes.